I see you haven't had enough chemistry yet. Good. I'm glad that you are here to do a difficult question. I'm not going to lie. Students generally have difficulty with common ion questions. So let's run through this one in as much detail as possible. This is on page 437. And I apologize if my house gets a little bit noisy. We have a lot of activity going on now. Okay, so I'm going to read you the question. The solubility of pure lead to chromate in water is 4.8 times 10 to the minus 7 moles per liter. A. Qualitatively predict how the solubility will change if lead to chromate is added to a 0.1 mole per liter solution of sodium chromate. So let's write our equation, or dissociation equation. And what's our stress to the system? We're adding sodium chromate. Now, is sodium a common ion? Well, in this equation here, you don't see it. But chromate, however, is right here. So what that means is that the stress to the system, according to Le Chatelier's principle, is an increased concentration of chromate. How are we going to relieve the stress of too many chromate ions? Well, we're going to increase the amount of lead to chromate solid by shifting to the right, which will decrease the concentration of lead. So solubility will decrease when sodium chromate is added to the system because of Le Chatelier's principle. Okay, the stress to the system is there's more chromate ions in the solution, and so it's going to relieve the stress by increasing the number of solid lead precipitate, or the amount of solid lead precipitate in the solution, and so that's going to decrease the solubility overall. So that's what the common ion questions are all about, is how solubility is affected by the additional ions that are in solution. So just think about in chemistry class, the labs that we did, we always use distilled water, and we use distilled water because we don't want the other ions within the water to affect our results. And sometimes they still do. But let's look at this example here. So for B, it's saying KSP for lead to chromate is 2.3 times 10 to the minus 3. Determine the solubility of lead to chromate in a 0.10 mole per liter solution of sodium chromate. All right, so let's set up our ice table, because we are going to need an ice table. We're dealing with a lot more information. So we have, nope, not carbonate. This is our dissociation reaction. And when I set up my ice table, again, I do not care about the solid. But now let's think about what's going on. If I was going to dissociate lead to chromate, I'm going to have 0 concentration of lead. However, it's saying that we're going to dissolve it in a 0.1 molar solution of sodium chromate. And we just identified that the common ion is chromate. So that means in our I part of our ice table, our initial part, we're starting at 0.10. Our change is going to be the same. You might be saying, well, you just told me that it's going to shift to the left and not, it's going to favor being solid. When we're dissociating from scratch the lead 2 chromate into an aqueous solution, we are saying that it's still going to be a forward reaction. However, it's going to be hindered by the fact that there's already chromate ions within the solution. And so we're not going to have as high of a solubility as what was given. And so remember, they said that the solubility of pure lead 2 chromate is 4.8 times 10 to the minus 7 mole per liter. So let's see, our prediction is that it's going to be less than this because of the additional chromate ions. So when I'm setting up my KSP, it's very lovely. We only have a 1-to-1 ratio. So my KSP is 2.3 times 10 to the minus 13. My concentration of lead is X. Oops, I forgot X plus 0.10. And then my concentration for chromate is, guess what? X plus 0.10. Now, I don't want to have to do quadratic. So let's do the 500 rule. Let's take 0.10, the concentration, and divide it by 2.3 times 10 to the minus 13. I don't have to do this on my calculator. I know that because I'm dealing with a very tiny number in my denominator, this is going to be far, far greater than 500. Do it on your calculator if you want to see it's going to be an astronomical number. So I get to simplify. I get to take out that X because of the 100 rule. So what am I left with? I'm left with, okay, I'm going to flip the equation. Okay, so 0.10 X equals 2.3 times 10 to the minus 3. I'm going to divide both sides. And I'm going to get, where am I? Sorry, I have everything written down. I should be able to do this in my head. Minus 12, that's right. 2.3 times 10 to the minus 12. And what does this represent? Do you see how this is a 1-to-1-to-1 ratio? This X represents the concentration of lead chromate that's dissolved in the solution. Now, I'll put in the other color. They said that pure lead 2 chromate, if it was in distilled water, this is what its dissociation should be. That's what its concentration should be in pure water. So just by having the addition of 0.1 molar of sodium chromate, it reduces the solubility of lead 2 chromate from 4.8 times 10 to the minus 7 moles per liter to 2.3 times 10 to the minus 12 moles per liter. What does that mean? Does it mean that it pushed the system to the right or to the left? It means that according to Le Chatelier's principle, and as we predicted in the first part of this question, it pushed the system to the left. It favored solid lead 2 chromate over aqueous lead 2 chromate, and it saw the reduction of the solubility from 4.8 times 10 to the minus 7 mole per liter to 2.3 times 10 to the minus 12 mole per liter. All right, so there are other questions for you to try, and these would be on page 439 and number 21 to 24. Try a couple of those ones. They're very important for universities. They're very important to think about in the context of this course too.